The topic we looked at yesterday, the law of conservation of mechanical energy, says that energy can't be created and it can't be destroyed. We talked about this yesterday, right? We said sometimes it looks like energy is created, it looks like energy is destroyed, but in the end it never is. The roller coaster going down the track, sometimes it looks like energy is created. A car is barely moving at the top of the track. By the time it gets to the bottom of the track, it's moving at 100 kilometers per hour or even faster maybe. Energy has been created, right? It's moving and it wasn't before. It's not created. It's been transformed from potential to kinetic energy. Sometimes when the car is driving on the road and slams on his brakes, comes to a stop really, really quickly, it looks like energy is destroyed. We had kinetic energy and now we have nothing. Well, it wasn't really destroyed. It was transformed from kinetic energy into thermal energy, maybe a little bit of sound energy. Sometimes you've got a sailboat in the middle of the harbor that's just sitting there. A big wind comes up and the sailboat starts moving. Energy was created, right? There was no energy in the sailboat. Now there's kinetic energy in the sailboat. Energy must have been created, but it wasn't. It was transformed from the kinetic energy in the wind to the kinetic energy in the sailboat. If we always take into account all of the energy that's present in the entire system, then we're always going to have the same total amount of energy at the end of the problem as we have at the beginning of the problem. Now, that manifests itself for us a lot in roller coaster type problems. Okay, we see a lot of problems that look like this, where a roller coaster is at the top of a track, top of a hill. We want to find the speed at the bottom of the hill. Or maybe it's the other way around. Maybe we want to find out how high this little car can go up the hill before it comes to a stop. Essentially, whenever we have an object experiencing a change in height, then we can use the law of conservation of energy to analyze that and find whatever it is that we're looking for. We do that always mathematically in the same way. We say EI is equal to EF. We have to include, for both the initial energy and the final energy, all of the types of energy that are present. Remember we said that sometimes it looks like energy is created, sometimes it looks like energy is destroyed. But if we account for everything, if we take into account everything, then it's not. It's just transformed from one type to the other. So you look at the beginning of the problem, EI, and you ask yourself a few questions. Is the object moving? If it's moving, then we've got kinetic energy. If it's not, then we don't include that. Is there a height at the beginning of the problem? If there is a height, okay, then we're going to say there's potential energy, which we add to it. Is there an elastic or a spring that's stretched or compressed? If there is, then we would add elastic potential energy to that, or spring potential energy to that. Now, it's not very common that we have to deal with that last one, but every once in a while, maybe it pops up. Ask yourself the same three questions at the end of the problem. Is it moving when the problem's over? Sometimes it will be, sometimes it's not. If there is, put in kinetic energy. 1F mvf squared. Is there a height at the end of the problem? If there is, put in mgh. If there's not, then leave it blank. Is there an elastic that's stretched or compressed at the end of the problem? If there is, then let's put in 1/2 kf squared. 1/2 kx squared, I should say. So that's the general form of our equation, really. Okay? Really, you could start off with that every single time. And if you don't have one of those types, you could just kind of scratch it out, make it zero. So far, so good? Most times, we don't have this type of energy. If we don't, there's always a shortcut that we can use to save us some time mathematically. What is that shortcut? Take off the mass. It appears in every term on both sides. We can cancel it out. If we added the 1/2 kx squared in there because it was an elastic or a spring, could we have canceled out mass? No, because it doesn't appear in every single term then. And you got to use the mass if you're dealing with, ironically, if you're dealing with elastic potential energy, which doesn't include a mass, that's when you have to pay attention to mass, when you're using a type of energy that doesn't include a mass. Okay, that's because it doesn't cancel out of that. All right, we had some questions for homework on worksheet number 5 last night. I believe it was 2, 4, and 5 that you need to go over. Was that right? 2, 4, and 5? Kathleen, was it number 2? Okay. Let's take a look Let's take a look at 2, 4, and 5 here. Number 2 says, a ball is dropped from a 60-meter high building. How fast is it moving when it's fallen halfway down to the ground? Here's my building, 60 meters. How fast is the ball moving at this point, halfway down, when it's 30 meters from the ground, basically, right? You could solve this problem using VF squared is equal to VI squared plus 2AD. Right? There's no issue with that. Okay, that would work fine. But that's not what I'd like you to do for this right now. I'd like you to be familiar with the conservation of energy analysis that we do. Let's say EI is equal to EF. It says it's dropped. If it's dropped, how fast is it moving when it begins? 0, right. If it's thrown downward, it's got an initial velocity. But if it's dropped, it's moving at 0 meters per second when the problem starts. How fast is it moving when it's fallen halfway down to the ground? Well, what kind of energy do we have at the top here before it's dropped, or as it's dropped? Do you have potential at the top? Yes, you do, right? Here you have potential because? Good. So it's set in mgh. That's gravitational potential, that is. Is there kinetic energy at the top? James? No, why not? Good, it's being dropped, it's not moving. It is after you drop it moving, right? But it's not as you drop it, not moving there. So there is no kinetic, and of course there's no elastic potential here because there's no spring or elastic in it. Halfway down. Is it moving now, halfway down? Is it? Yeah, so it's got kinetic energy, right? 1/2 mv squared. Does it have a height halfway down? Yes, so it's got mgh. And there's still no elastic or spring. Cancel out the masses here. It's good because we're not given a value of the mass. 60 meters, right, for the initial height. The final speed is what we're looking for there, the speed halfway down. Plus 9.81 times the, what's the final height here halfway down? Kathleen, what's the final height there? 30 meters, good. 9.81 times 60 is 588.6. Plus 294.3. Take that over by subtracting. I get 294.3 equals 1/2 VF squared. Take the half down by dividing. I get 588.6 equals VF squared. We square root that. And VF is going to be equal to, I don't know, 24. How did I say? What does that work out to be? Somebody have that? Yeah. 24.3 meters per second. Good. Is there anybody that did this question slightly differently, but yet still using energy? You did? How'd you do it? Who else did it that way? Who else said mgh equals 1/2 mv squared? Okay, Kathleen did. mgh equals 1/2 mv squared. Ryan did. Okay, Spencer did. How can we do that? How can we say this gets us the right answer when this gets us the right answer, and it's two different ways, it's two different setups? How's that possible? What do you got to do to make this work? Go ahead. Change the initial height to 30, yeah. If we're defining everything relative to this, remember we said when we started energy, we can define potential energy relative to whatever we want. Relative to my hand, the potential energy of the pen is 0. Relative to the floor, it's something, right? We can define the potential energy as 0 relative to the ground or as 0 relative to this. If we define it as 0 relative to this, then our initial height isn't 60, it's 30. And when you solve for VF there, it's still going to work out to be 24.3 meters per second. That make sense? That make sense, guys? All right. I want to show you one more quick little thing. Did anybody, by the way, use VF squared is equal to VI squared plus 2AD for that? Okay, good. Okay, on a test, I'm fine with you doing that, okay? But in the end, on this, I want you to do it. I want you to do EI equals EF just as practice so you become familiar with it. But I want to show you something real quickly. Okay, let's say we did do VF squared is equal to VI squared plus 2AD. Let's take the equation that we set up right here and change it around a little bit. Okay, I'm going to get rid of this. Okay, we got G times HI. We got G times HI is equal to 1/2 VF squared plus G times HF. Okay, let's rearrange that and see what we can do with this. Okay, let's take the G times HF over by subtracting. Actually, let's not use this form of it. Let's use this form of it over here, okay? We're going to say here that VF squared, let's take that 1/2 over by dividing, becomes G times HI over 1/2 equals VF squared. VF squared is equal to 2 times GHI. Make sense? That looks a lot like this, right? What's VI? What's VI there? What's VI in this problem? All right, let's take that out. So VF squared is equal to 2 times A times delta D. VF squared is equal to 2 times G times HI. What's G? Acceleration. What's H? Effectively the displacement of the ball as it drops, right? So if you use VF squared is equal to VI squared plus 2AD, isn't it really the same thing as using conservation of energy? You're just not thinking of it in the same way. Of course you're going to get the same answer. It's the same thing. In fact, that's really where this equation even comes from in the first place. We just didn't tell you that when we taught you that equation because you didn't know anything about energy then. All right, next question was number 4, I think, wasn't it? 4 says, a javelin is thrown at a speed of 20 meters per second at an angle of 30 degrees. A short time later, the javelin has come back down and stuck in the ground. Describe the energy conversions that are taking place. Here's the javelin, 30 degrees. It goes up, and then it comes down and sticks back into the ground. What are the energy conversions that are taking place? Well, as it's released, what kind of energy does the javelin have? Kinetic energy, right? What happens to the kinetic energy of the javelin as it goes up into the air? It decreases because it slows down. What happens to the potential energy as the javelin goes up into the air? Increases. So you've got a conversion taking place initially of kinetic to potential energy. The javelin goes up, kinetic energy decreases, potential increases. You're converting kinetic to potential. What happens when it reaches its max height? Well, vertically it stops. Yeah, horizontally it doesn't, but vertically it does. That's when your potential energy is maximized and your kinetic energy is minimized at that point, right? As it starts coming back down, what happens? Now you don't have a conversion of kinetic to potential. Now you have a conversion of potential kinetic. So it's as simple as saying, as the javelin goes up into the air, there is the kinetic energy of the javelin converted to potential. As it comes back down, there's the potential energy of the javelin being converted back into kinetic. All right, finally, let's take a look at question number 5 on that same worksheet. It says a 0.75 kilogram ball was thrown straight up into the air. The ball reaches a max height of 17 meters before it comes back down. What was the initial speed of the ball? This is a question similar to one we did yesterday, right? as an example. The ball was thrown up into the air. We don't know how fast it's moving when it's thrown up into the air. We got to find that speed. It goes up, it reaches a max height of 17.0 meters. And then it comes back down. What's that initial speed? Let's say EI equals EF. EI we're going to define as when the ball is released. What kind of energy does the ball have when it's released? Is it moving? Yeah, not before it's released. Okay, that's a whole other question. After it's released, it has kinetic energy. Does it have potential energy after it's released? Immediately after it's released, that is. No, it's got no height. When it reaches its peak height, that's where we're going to define as our final point, right? This is initial down here. This is final up here. What do you got up there at the end? What kind of energy do we have at the end of the problem there? Potential, because it's got a height. Does it have kinetic up there? No, it stops. So we just got kinetic is converted to potential there. M's cancel. We're going to say 1/2 of VI squared. Take the half over by dividing. And now let's square root that. So it becomes 9.81 times 17 divided by 1/2. That's going to give me somewhere in the range of, I'm going to say, I don't know, 16? What's the answer there? We get 18.3 meters per second is the initial speed. Good? Thank you, Louise. Good? All right. I want to take a look at one more problem here, number 6. We'll do this one as a group. It will show you how even when we're dealing with an elastic or a spring, it's really the same problem, really the same type of conservation of energy problem. And then once we're done that, we're basically done this unit. Just going to give you some practice. A spring with a spring constant of 200 newtons per meter is compressed to 25 millimeters. If a 1 kilogram object is attached to the end of the spring, what's the max speed of the object? In other words, how fast is the object moving when you release the spring? You guys have all done that before, right? Take an elastic, you stretch it, and then let it go. It's potential energy stored in the elastic when you stretch it, converted to kinetic energy when you release it. That's what we've got going here, right? EI is equal to EF. The initial is when the spring is compressed. What kind of energy do you have when the spring is compressed? Not gravity potential, not kinetic energy, but rather elastic potential, somebody says. 1/2 kx squared. After it's released, when it reaches its maximum speed, what kind of energy do you have? Kinetic. Anything else? No, it doesn't say anything about going upwards, so we're not going to say anything about gravitational potential, okay? Do you have elastic potential or spring potential still at this point? No, think about that. If you did have spring potential still, then it wouldn't be at its maximum speed. If you still had spring potential energy, then it could still move faster because you could have more conversion taking place from potential to kinetic. And once it's reached its maximum speed, there is no potential left anymore. All right, can I cancel out mass there? No, you can't. Yep. Is it 1 kilogram? Yeah, it is 1 kilogram. So yeah, we're still not going to cancel that. Mathematically, it ends up being the same thing as canceling it, but I don't want you to go through that process because I don't want you to be tricked if it's not 1 kilogram next time, right? There is something that we can use to simplify this a little bit, though. It doesn't help a lot, but yeah. Yeah, you can get rid of the halves because a half appears in every term. That makes sense? What's the spring constant? 200. The displacement here is 25 millimeters, so that's 0.025 meters. Square that. The mass, as Tara said, is 1 kilogram times VF squared. Let's get the calculator for this one here. What do we got here? Let's bring it over here. We got 200 times 0.025 squared. Let's divide that by 1, which is still the same thing. Now let's square root that. I get 0.354. Remember I told you guys when we started this unit about those toy guns we used to make when I was a kid? We'd go out in the woods behind my house and shoot them at each other, shoot these little springs from clothespins at each other. Remember that? Yeah, I did. Yeah. Maybe you weren't here. In the end, we had no idea. We had no idea when we were kids how to figure out how fast these projectiles were that we were launching at each other, right? But now, I realize it's a pretty simple calculation. If we knew what the elastic constant of the elastic was, and that would be a pretty easy thing to find out, actually, the elastic constant or the spring constant of the elastic, then we could pretty easily determine how fast the little inside of the clothespin spring was going to be moving when it was released. It's just 1/2 kx squared equals 1/2 mv squared. Solve for v. Okay. This one isn't moving very fast, 0.354 meters per second. You can imagine if one of those little springs is moving at, 15 meters per second, then all of a sudden it's going to hurt quite a bit. Good? Make sense? Excellent. So we have our unit test on Tuesday, our mini unit test just on energy. There's only a few topics that we've really done in this kind of subsection of a unit. We started off the unit with the definition of energy, right? The types of energy as well. We had kinetic and we had potential. And within potential, can't spell potential, but we had it. Within potential, we had elastic potential energy or spring potential energy, and we had gravitational potential energy. And of course, gravity is the one that we focus on the most, although we do see elastic potential energy as well. Okay, kinetic energy was given by the equation EK is equal to 1/2 mv squared. Elastic potential energy was given by the equation EP is equal to 1/2 kx squared. And every once in a while, whenever we found elastic potential energy, we had to find K using some other method. That other method we call Hooke's law. Remember, F is equal to Kx, and then we just simply rearranged it to solve for K to plug back into here. Don't have to do that often, but from time to time we do. We also had gravitational potential energy, which of course EP is equal to mgh. Remember, that's the kind of energy that we said we can always define relative to whatever we want, really, whatever's convenient there. What do we do after we talked about energy and the types of energy, kinetic and potential energy? We talked about work. Work is the change in energy. Okay, we need to know the definition of work. The change in energy. The work energy theorem. In the end, the work energy theorem is simply this relationship. W is equal to delta E. And of course, we also had to know the equation for work. W is equal to F times D. Sometimes F times D times cosine theta, sometimes just F times D. When do we drop the cos theta? When is it okay to make it just F times D? If theta is 0, in other words, if it's pulled in the same direction as it moves, then we can say theta is 0. If you pull a wagon at 30 degrees and it moves at 0 degrees, well, you got to take into account the angle. If you push a box horizontally and it moves horizontally, you don't have to take into account the angle because the angle is 0, and cosine 0 is just equal to 1. What do we do after work? We said, I can't remember who it was that we used as examples. Shoveling the driveways. Who were they? Garrett, I think, was one, right? No? Oh, Quinn and Spencer, that's right. So Quinn and Spencer were shoveling the driveways. We didn't care how much work they did. They both did the same amount, right? We cared about how quickly they did it. How quickly they do their work is power, right? How powerful they are. So the next thing we did was power. Generally, if you're pretty good at doing work, you're going to be pretty good at doing power because power is just a simple extension, right? It's work over time. Just do work and then divide it by time. So we see it written sometimes as power is equal to W over delta T, but in the end, sometimes we make it delta E over T as well. Listen, if you don't have the value of W or delta E, then get it. Get it using number 2 here. Get it using the way that we solve for work, and then just simply divide it by time. Finally, what do we do after power? Last topic. Conservation of energy. Okay, you got to know what conservation of energy is. But in the end, the biggest thing with conservation of energy is just do it. The total amount of energy never changes. If we account for everything, the total amount of energy that we have at the beginning of the problem is always equal to the total amount of energy that we have at the end of the problem. Does that make sense? All right. Good news. We're finished the unit. And there's only the subsection of this unit, and there's only 4 topics. Okay, this should be a nice test to study for because you don't have to worry about a million different things. It's 4 little things. More good news. I got a couple worksheets for you here that we just handed out, 3 worksheets, in fact, that we just handed out. There's examples of each of the types of problems on these 3 worksheets. Okay, we're going to spend the next 20 minutes today working on these 3 worksheets. We'll see how far we get with them. Any questions? Call me over. Ask for help. This is your opportunity to prepare yourself well for this test. Okay. We'll see how far we get today, whether we assign any of it for homework or what. But in the end, get as far as you can. Work as hard as you can at it today. Ask me those questions, and use this time to prepare for that test on Tuesday. Okay. All right. Let's get at it.